Welcome to Physics 2101, a course in mechanics. Mechanics is the study of motion, and this course is divided into the following main sections: study of linear motion, circular motion, rotational motion, and oscillatory motion, mainly oscillations and vibrations, which we will study towards the end of this course. Now, throughout this course, we will use particle model, where any object which is in motion is represented by a simple particle, and then develop the model for the rigid body model for motion, where we will describe motion of rigid bodies, not just particles, but solid bodies, extended bodies. Now, with each one of these sections, there will be two main subsections. The first subsection is kinematics, and kinematics is a mathematical description of motion. Kinematics describes how objects move, and dynamics associated with that form of motion. And dynamics describes why objects move in the particular way that they do. For example, if you were to drop a rock from top of a cliff, as you know, the rock will follow a linear trajectory down towards the ground. Kinematics describes the motion of the rock as being a linear fall downwards, and dynamics of this motion describes why the object follows that linear motion downwards. So with each one of these categories here, linear, circular, rotational, oscillations, vibrations, we will cover both kinematics and dynamics of that motion. Now, to describe motion, we will describe motion in terms of a position vector. Position vector R, which describes the position of the object, as the name infers, velocity vector V, and acceleration vector A. In each case, for each motion, we have to choose a suitable coordinate system So if we are to describe the motion of a car moving to the right, let's say that this is our road and here's our car, and it's moving to the right. A suitable coordinate system, of course, is a simple x-axis, where we choose the origin to be the initial position of the car, for example, and we represent the car by a simple dot. So this is our particle model. Your object can be a car, a ball, an elephant, a table, whatever it is. You represent that by a simple dot, and then you show the motion of your object by showing the position of the object, once again using the particle model, at equal time intervals apart. So if the car, let's say, is moving to the right with a constant speed, so it means that if the time interval between each dot that you draw you choose to be 1 second, for example, it can be anything so long as the time intervals are constant. So if the interval is 1 second, then as you see, the position of the car increases by 1 division to the right at each interval. Now, the x-coordinate system that we've shown here by virtue anything to the right of the origin has a positive x value, anything to the left has a negative x value, and had you chosen your x-coordinate to be pointing to the left, this is your origin, and anything to the left of the origin would have had positive value, anything to the right would have had negative value. So where you position your x, the label, shows the positive of the axis. In the case of a linear motion in the vertical direction, that falling rock, for example, of course a suitable axis would be the y-axis. This is our origin, and let's say our cliff is 30 meters high and the rock starts at 30 meters high. Experience tells us that as the rock falls, it picks up speed. So as the rock nears the ground, then the distance between each dot, which once again, let's say each dot is 1 second, shows a 1 second interval, the distance between each dot increases due to the fact that our rock is picking up speed as it falls towards the ground. And in this case we've chosen our coordinate system with the y-axis pointing up, which means anything above the origin has a positive value, anything below the origin has a negative value. These examples are examples of one-dimensional motion. In the case of the car, the position is given by the x-coordinate. Velocity is simply the x-coordinate of the velocity vector, and acceleration is the x component of the acceleration vector, or ax. In the case of the falling rock, position is given by y, velocity vy, and acceleration ay. And of course, whether you have a positive or a negative value is determined by your choice of the coordinate. Excuse me. In the case of a two-dimensional motion, of course, a suitable coordinate system would be an xy coordinate system. So here, once again, anything to the right of the axis is a positive x, above the coordinate is positive y, etc. Now in some problems you may find it more suitable to choose your x pointing to the left, which is perfectly acceptable, but just do remember that when you label your x pointing to the left, that means anything to the left of the axis assumes a positive x value.